Hi, welcome to the audio introduction for Lab 4. In this lab, we're going to focus again on the textures and classification of rocks. So the main focus is on using the commonly used schemes of classifying igneous, metamorphic, and sedimentary rocks. And in addition, we will also look at some sedimentary textures and discuss as to how that can tell us about the conditions of deposition. As the classification scheme for igneous rocks was discussed in detail in one of the audio lectures that was posted on Blackboard as part of the lectures, and so I'm not going to discuss in detail that classification again, but it's suffice to remind ourselves that the classification of igneous rocks is primarily based upon the compositions of minerals that are present in the rock. In general, we can identify 4 different groups: felsic, intermediate, mafic, and ultramafic rock, with felsic minerals dominant in felsic rocks and mafic minerals dominant in ultramafic rocks, and the felsic to mafic ratio decreases as you go from a felsic rock to an ultramafic rock. Okay, the other factor that's considered in this classification is the mode of emplacement of the igneous body, whether it is intrusive, which is characterized by a phaneritic texture, or whether it is extrusive, which is characterized by an aphanitic texture. So a felsic igneous rocks that primarily contains alkali feldspar, quartz, plagioclase feldspar, and a little bit of mafic minerals. If it's intrusive, it's called a granite. If it's extrusive, it's called a rhyolite. So likewise, a mafic igneous rock that's composed primarily of plagioclase feldspar, some olivine, and pyroxene would be called a gabbro if it's intrusive, and called a basalt if it's extrusive. So we can say that the rhyolite is the extrusive equivalent of granite, and basalt is the extrusive equivalent of gabbro, or granite is the intrusive equivalent of rhyolite, and gabbro is the intrusive equivalent of basalt. Okay. One of the other things that you're going to be doing in this lab is to look at cross-cutting relations to establish a relative time of formation of rocks. And you're going to be using map patterns to figure out whether or not rock units are older or younger relative to each other. So as an example, here we have an image on the left that actually shows 3 different rock types. So a darker igneous rock, a light colored igneous rock, and a third igneous rock that's sort of intermediate between the first 2. So when you look at the field relationships here, what we see is that the rock unit 1 is cut by rock unit 2 and 3, and hence the rock unit 1 is the oldest of them all. Now when you look at the field relationship between 3 and 2, you see that the rock 3 is cutting across rock 2, and therefore the rock unit 3 is the youngest unit. So therefore the rock unit 2 is of intermediate age between 1 and 3. Okay. Another thing to keep in mind for this lab is the definition of a dike and sill. So we defined a dike as a tabular intrusive body if which cuts across the layering of the country rock, so such as shown in this case. Whereas if you see an intrusive body that's generally parallel to the contacts of the country rocks, then we would use the term sill. Okay, moving on to metamorphic rocks. So again, we have discussed the scheme of classification in the audio lecture as part of the lecture that was posted on Blackboard. In general, we can classify metamorphic rocks into two broad types. Those that exhibit a foliation are foliated rocks, and those that do not exhibit any foliation are non-foliated rocks. Further, the foliated rocks can be classified based upon the percentage of orientable minerals. So typically foliation results from the parallel alignment of micaceous minerals or platy minerals. So orientable minerals here refer to the micaceous or platy minerals. A factor in classifying the foliated rocks is whether the orientable minerals dominate the rock, so that is more than 50%, or if they are subordinate compared to other minerals that are present in the rock. Okay, and depending upon and for rocks that are dominated by orientable minerals, there are three possible kinds: slate, phyllite, and schist, and the distinction between them primarily is in the grain size, and I'll discuss that in detail in the next slide. So a slate is a metamorphic rock that is foliated, so it shows a really well developed foliation, and the foliation is so perfect that the rock has a tendency to break along those foliation planes, just like minerals break along cleavage planes. And the other feature of slate is that the grain size of the rock on average is microscopic or submicroscopic. In other words, you're not going to be able to distinguish individual grains with your eye or even with the help of a hand lens. Okay. A phyllite, on the other hand, is a bit more coarse grained, as shown in this image, with the result that you can identify a few grains with your hand lens. Okay. That said, perhaps the best way to distinguish between a slate and a phyllite is to look at the surface of the rock and to see whether the rock exhibits a sheen. So the surface of the shale appears fairly dull, whereas the phyllite appears shiny, or there is a silky sheen on the surface, and that's primarily because the grain size in phyllite is coarser, which enables the grains to reflect light a bit better, making it appear brighter and more shiny. Okay, so then to recap, then the distinction between the slate and phyllite is that the phyllite is slightly coarser grained. Okay, in all other respects they can look very similar, so they both have very perfect foliations. Now, if the grain size is coarse enough that you can identify the grains with a naked eye, and if the rock is foliated, so I realize that in this image we are actually looking down a foliation plane, so to actually see the foliation planes, so you have to look along the side to actually see the foliation planes. Okay, but it's obvious that the grain size is coarse enough that we can identify individual grains in this rock, so we call such a metamorphic rock schist. So a schist is a foliated metamorphic rock in which the grains are coarse enough to be identifiable with your naked eye. Here's another example of schist. It shows a partly broken surface. So in this phase we are actually looking down the foliation plane, so we're just seeing the reflection from the foliation planes. However, here is a broken fragment which actually shows the foliation plane. So one of the things that you would notice with most schists is that the foliation is less perfect than in the case of a slate and phyllite. Okay, and that's a function of the grain size getting coarser and having other minerals in between, so the foliation loses its crispiness. If the foliated metamorphic rocks contain only less than 50% micaceous minerals or orientable minerals, typically it results in a foliation being less perfect and less continuous. So as you can see from the image here, it has a rather well-defined foliation planes, but if you were to track the foliation plane along, you will see that it kind of breaks up. It's not that continuous as in the case of the other three rock types that we've looked at so far. Okay, and that's typical of gneiss. Okay, and the reason for that discontinuity in foliation is because in gneisses you have less than 50% orientable minerals, and in particular you have other minerals like quartz and feldspars, which are not really orientable, forming a bulk of the rock. Okay, and one of the other textural features that results from the abundance of quartz and feldspar is that the rock has a banded appearance, as is shown here by layers of dark colored minerals, so in this case likely biotite, and other layers that are dominated by quartz and